So now I'm going to switch roles from moderator to speaker and switch hats from representing the Embedded Vision Alliance to representing BDTI, which is my day job. And I'm going to give a presentation about tools for embedded vision. This is going to be a little bit different from the style of the presentations that have gone before, which have mostly drilled down deep on a particular algorithm or methodology or architecture. Here I'm going to do kind of a survey, an overview of some, what I consider to be some of the most interesting recent developments or current developments in tools and libraries and other application development infrastructure for embedded vision applications. Are we ready to go on the mic? Okay, great. So switching mics as well. So, my background is as a DSP engineer, developing digital signal processing applications and especially optimized architectures and optimized software to implement digital signal processing applications and algorithms across many different domains: audio, wireless, speech, video, and over the past few years also computer vision and embedded vision. One of the things that's unique, Phil, if you caught Phil's comments earlier about BDTI, one of the things that's unique about BDTI is that we do both evaluation, benchmarking, and analysis where we look across a cross-section of alternative technologies for a given problem. We also drill deep into individual technologies and applications as part of our engineering services work. So some clients hire us to help them select A versus B versus C, whether that be a processor or tool or an algorithm. Others hire us to implement a specific algorithm or application and optimize it on a specific architecture. So we get the opportunity to look across a range of technologies and applications, and also to get really into the low-level details and get hands-on with the technology. And that's some of what's informing that work that we do every day for our clients is largely what's informing this presentation and our perspective on tools for embedded vision. So I want to emphasize that this is not a presentation on behalf of the Alliance. This is a presentation on behalf of BDTI and represents our views on the topic. So the first thing I want to say about tools for vision is there are many of them, and many of them are moving quickly. And the first thing to think about is where in the kind of life cycle or design cycle of an application you are, because there are tools that are very strong for early kind of prototyping, proof of concept, rapid experimentation on the desktop. There are tools that are very good for the optimized implementation on a specific architecture. There aren't very many tools that span that whole range. So often what you're going to have is a collection of tools, and as you move from the early stages to the later stages of the design and implementation process, you're going to start using some tools more and other tools less. So for example, I'm going to talk about OpenCV, and historically OpenCV has been very strong for the front end of the design process. It's been kind of like a MATLAB-like tool to enable very rapid experimentation with algorithms, but it hasn't been used as much for implementation, although it has been used some for implementation. So understanding where you are in the development process is critical to figuring out which are the right tools to be using. And there are some big trade-offs among the tools options. And I think this chart summarizes some of the most important trade-offs. For example, when we're writing code, we'd like the code to be really easy to write, so productivity is high. We can very quickly get the code written. We'd also like the code to be very, very portable, so we can delay the choice of processor or make a different choice of processor halfway through the project without it having a very disruptive impact. And you can get those things. You can write code in a way and use tools that allow very high productivity and very high portability. But if you do that, you're going to be giving something up. And the something that you're going to be giving up first and foremost is probably efficiency, especially when you get to the implementation. If you need an efficient implementation, if you need to optimize for cost, power consumption, size, and so on, then you're almost certainly going to have to give something up by way of productivity and portability. So that's one of the fundamental trade-offs, and there are a number of others. And where you want to be, this is also part of why different tools make sense for different stages of the design process, because early in the design process, for example, there's usually a premium on rapid experimentation. Let's figure out if this thing's going to work, what approach is going to work best. And so we'll give up efficiency. If we have to use a big rack of GPUs to get a real-time prototype, that's okay. But then as we start getting closer and closer to implementation, that's not okay anymore. Now we need a focus on efficiency, and so we're going to shift to different tools and techniques that are going to give us better implementation efficiency, but we're almost certainly going to sacrifice productivity and portability. OpenCV has already been mentioned a few times today, including in Goxel's talk. OpenCV, I think, is kind of like the grandfather of vision tools and libraries. If you're not already familiar with it, it's a large open source software component library for computer vision. It started out as an Intel project, as a proprietary Intel library, and then turned into an open source project. The guy who's been behind the project from the beginning, Gary Bradsky, started the OpenCV Foundation a year or so ago to oversee and raise money for ongoing development of the library. It's got many, many users, a very active community. It's very actively being evolved. So these are some of the key advantages. It's big. There's a lot. There are a lot of functions in it. It runs on multiple operating systems, and of course it's free. It's open source, and it's open source with a very liberal license, the BSD license, which means you can use it in your product, and you're not required to then make your own product open source. So most companies consider that to be an acceptable form of open source versus something like GPL, where if you use it, you then have to make your own source code open source. On the other hand, it's not perfect. As Goxel pointed out, not all of the algorithms are best in class, and the quality isn't always great. There are, but it's not uncommon to find bugs, and sometimes there's maybe an emphasis on getting things in the library, getting OpenCV to be bigger and more comprehensive over making sure everything that is in there is really robust. On the other hand, since it's provided in source code, you at least have the opportunity when something goes wrong to figure out what's gone wrong and to debug it yourself if you're willing and able to do that, which isn't always the case with commercial libraries. Sometimes, and I'll talk about commercial libraries later on that are processor specific, sometimes those libraries are not provided with source code. So if there's a bug, well, the good news is there's a commercial entity behind it, presumably to back it up and fix the problem. The bad news is you can't fix it yourself because you don't have the source code. And of course, a further advantage of having the source code is you can learn from it, study how the code is written, and you can customize it. You can modify it for your own purposes. OpenCV has been moving quite fast lately in terms of new versions. And the latest version, the newest version, version 3.0 is due out, I think, in the next few days, with many enhancements and improvements and additions. In our opinion, the most significant one is the support for transparent acceleration using OpenCL. And I'm going to talk about OpenCL in a minute, so I won't get into too much detail on it here, but what I'll say is OpenCL is a parallel processing language that's being supported on more and more parallel processing architectures. And what the OpenCL capability of OpenCV enables is that when OpenCV is run on a target processor that supports OpenCL, it can automatically use OpenCL to run faster and use that parallel processing capability. That's potentially a really significant feature because it gets us, it improves that trade-off that I mentioned where, okay, we're using this large, fairly easy to use library, gives us good productivity and portability, but now we also can get some parallel processing optimization out of it kind of for free without having to go in ourselves and recode OpenCV functions to exploit features of specific architectures using OpenCV as a kind of intermediate layer that enables using OpenCL as an intermediate layer that enables OpenCV to access parallel processing capabilities of multiple processors from different vendors and so on. Now, this is not a new concept. Parallel processing optimization in OpenCV people have been doing this for a while. For example, there are optimizations for the ARM Neon, single instruction, multiple data, extensions that are found in all the high-end ARM processors that are in mobile application processors for cell phones, for example. There are optimizations for CUDA, which is NVIDIA's proprietary general-purpose GPU language. There are optimizations for x86 using the single instruction, multiple data capabilities in x86 architectures. But what is different here with OpenCL is that OpenCL is cross-platform. It's not specific to an individual processor supplier's instruction set architecture. So that's a significant improvement in OpenCV. So now let me talk about OpenCL. OpenCL is, and this is an important difference, people often get confused between OpenCV and OpenCL, which is understandable since alphabetically they're very similar. Where OpenCV is not a standard, I should have mentioned that a minute ago, it's an open source project. There's no formal process for deciding what goes in and what goes out and how the APIs should work. It's a little bit free form. And that has pluses and minuses. Oftentimes for industry, for commercial enterprises, the lack of a standard can be considered a negative because it's hard to have confidence in where things are going and being able to maintain compatibility and support an investment on an ongoing basis. You know, maybe other people in the group decide to take it in a different direction. OpenCL, in contrast, is a standard. It's a standard promulgated by Kronos, which is a not-for-profit industry consortium that has developed many industry standards, the most widely known of which is probably OpenGL, which is a 3D graphics API. The idea of OpenCL, as I mentioned earlier, is it's a parallel processing language and API. It comes from the general purpose GPU space. I have another presentation at the end of the day in the other track where I'm going to talk about processor architectures, and I'll talk more there about general purpose GPU. But the basic idea is that graphics processing units are increasingly being used as massively parallel single instruction multiple data processors to do work other than 3D graphics. And image and video and vision problems are often really well suited for that kind of data parallel architecture. When I mentioned CUDA earlier, CUDA is NVIDIA's proprietary language and architecture approach for GPGPU. OpenCL is an industry standard approach to GPGPU programming, but it's not limited to GPUs. It can be implemented and is being implemented on other architectures, other kinds of parallel architectures, like DSPs, for example. Even multi-core CPUs and FPGAs are now starting to support OpenCL. So OpenCL, while it's not vision specific, there's nothing in OpenCL that talks specifically about vision applications, it's a nice fit for many vision applications because many vision algorithms are highly data parallel. We often, as I mentioned in my introductory remarks this morning, need to use that data parallelism, map the parallelism of the algorithms into parallelism in the architecture to get an efficient implementation of our application. And OpenCL is a tool for doing that. And as I mentioned with OpenCV, OpenCL can interface with other tools and libraries and abstractions. So for example, OpenCV now has this OpenCL layer, so to speak, so that OpenCV functions are implemented in OpenCL. And so when OpenCV code runs on a platform that supports OpenCL, it can automatically make use of the parallelism without the software developers having to manually recode those functions to take advantage of the parallel architecture capabilities. OpenCL 2.0 is the latest version of OpenCL. It was just, the standard spec was just released in November, so about 6 months ago. And it introduces a number of features that help to improve the performance and the flexibility of parallel processing applications implemented in OpenCL. In particular, enabling tighter coupling between the main CPU and the GPU, or whatever the parallel coprocessor is. And by the way, I should mention that that's kind of a fundamental idea behind OpenCL, is that there is a processor-coprocessor architecture. There's always a CPU, typically either x86 or ARM, coupled with some kind of parallel coprocessor or coprocessors, most commonly a GPU, but not necessarily a GPU. There's a related effort called heterogeneous system architecture, which I'll mention in a minute. But let me first say a few more things about OpenCL. I think the biggest plus about OpenCL is that it is portable. It's an industry standard supported by many vendors. Unlike some of the other things like ARM Neon or NVIDIA CUDA that are strictly limited to those suppliers' architectures, OpenCL spans multiple vendors, multiple classes of architecture. Historically, this kind of language, this kind of SIMD programming paradigm, like CUDA and OpenCL, has mainly been used in high-performance computing kinds of applications, like data centers, supercomputer applications where people are doing things like oil exploration, seismic analysis, and high-frequency financial trading and things like that. But as the parallel processing capabilities of mobile and embedded processors have been expanding, now OpenCL is being supported on mobile and embedded processors. And this is something that's just started to emerge in the last maybe 6 months, and it's still not fully supported everywhere. But I think this is one of the things that makes it a really significant development from the perspective of embedded vision. Given that we often need to use parallel processors to get a good efficiency for our vision applications where we have cost, size, and power constraints, being able to do that in a way that is, at least to a significant degree, vendor independent, processor vendor independent, and architecture detail independent is potentially very attractive. HSA Foundation is a separate industry consortium, independent of OpenCL, but related to OpenCL. This was spearheaded by AMD. It's also targeting this heterogeneous compute idea, but taking a slightly different approach, including having a hardware architecture specification that ensures tighter coupling between the main CPU and the GPU or other parallel coprocessor. As you probably know, a common problem in processor-coprocessor architectures is that, yes, the coprocessor runs a piece of the workload much faster, but the overhead associated with moving the data from the processor, the main processor, to the coprocessor and then back as they share the workload, if you're not careful or if you're unlucky, can negate the gain that you hope to get by running a certain portion of the code faster in the coprocessor. And so a way to combat that risk is by more close coupling between the main processor and the coprocessor. And one way of implementing that is by having a shared memory space. And that's part of what the HSA Foundation specifies in their hardware architecture spec and supports in their software tool stack and API. There's some overlap between the HSA Foundation functionality and OpenCL, but there's also some complementary aspects, and OpenCL can be implemented on top of the HSA Foundation spec. At least that's conceptually the idea. OpenCL is much further along than HSA. HSA is pretty new. The HSA Foundation has not yet issued the 1.0 version of their spec, although there's been some early efforts to implement some of the functionality. So we have to wait and see how widely it's going to be adopted and how much processor vendors in particular are going to invest in it. But from the point of view of embedded vision, this is a good thing. It's another good thing like OpenCL, especially if it gets widely adopted, because it helps get efficient parallel processing. Helps enable us to get efficient parallel processing, again, mostly for data parallel, single instruction, multiple data kinds of algorithms, in a way that's less processor vendor specific, less processor device specific than previous ways of implementing parallel processing. Yet another open blank blank is OpenVX. There's actually going to be a presentation on OpenVX by Neil Trevitt of Khronos later this afternoon, which I encourage you to see. Khronos, the same organization that has done OpenGL and OpenCL, is now doing OpenVX. They've released a provisional specification late last year, whereas OpenCL is not vision specific. It's a general parallel processing standard for data parallel applications. OpenVX is explicitly vision specific. So OpenVX is a hardware abstraction API that is vision specific, that's designed to specify an interface so that programmers who are specifically developing vision applications and algorithms can write their algorithms in terms of the OpenVX API and library blocks and programming paradigm, and then get efficient implementations on a wide variety of processor architectures where the details of the hardware implementation are hidden from the programmer by the OpenVX interface. So OpenVX has a notion of building block functions, specific vision functions, and a notion of a pipeline where the programmer constructs a pipeline of vision functions and data flows from some input through a first function, then directly into a second function, through that into a third function and so on. The idea being that there can be a very streamlined implementation on a very optimized hardware architecture without having to keep moving data back and forth between a CPU, a general purpose processor, and one or more co-processors and incurring a lot of overhead. So the idea is that you can specify a block diagram, in essence, for your vision application or algorithm, and then it's up to the hardware to implement it in the most efficient manner possible, hiding the details from you as the programmer through this OpenVX abstraction layer. If the hardware doesn't implement a particular function, then it may just wind up being implemented on the general purpose CPU, but you don't have to worry about the details. It's up to the OpenVX implementation to implement your graph in the most efficient manner possible, given the capabilities of the hardware. Now, this is very new. The first version of the standard, official release version of the standard, isn't even out yet. So there are no implementations of OpenVX on processors. It's not clear how widely it will be adopted. Certainly, many companies in the industry, processor companies, tools companies, and even end product companies were involved in the development of the OpenVX standard, including my own company, BDTI. So there's been a lot of industry interest in developing this standard, but we need to wait and see how widely and how extensively, how deeply vendors are going to invest in it, specifically the silicon vendors. If they do invest in it, I think it's going to be a good thing. And the way I think about it at the top level, why it's a good thing, is it offers to relax this trade-off that I mentioned earlier between productivity and efficiency and portability. If OpenVX is widely adopted and well implemented, developers will be able to write very portable code at a pretty high level, in other words, high productivity for software engineers, but still get very efficient implementations and be able to move their code from architecture to architecture without having to rewrite it. So that's very promising, but we have to see how that promise will be realized and if it will be realized by widespread adoption of OpenVX. Again, if you're interested in OpenVX, I encourage you to see Neil Trevitt's presentation later this afternoon. Another very important tool is processor-specific libraries. We already talked about OpenCV, which is not processor-specific, although there are variants of it that have been tuned for specific processors. By processor-specific libraries, I mean things like the TI VLab, a library that Goxel mentioned. And this is not a new idea. In fact, Goxel and his team started developing TI's library in 2008, so 6 years ago. But with increasing interest in vision applications and a growth in the number of processors targeting vision, whether they're vision-specific processor architectures or other kinds of processors like GPUs or FPGAs that are now being targeted for vision, more and more of these vision-specific libraries are emerging. For example, at NVIDIA's GPU technology conference a couple of months ago, NVIDIA announced a new vision library called VisionWorks for their new mobile application and embedded processor called Tegra K1. CEVA, who we're going to hear from later this afternoon, CEVA has a licensable processor core for vision and imaging called the MM3101 and has a really large library with almost 1,000 functions for embedded vision that are optimized for that architecture. These are what I call building block function libraries, relatively low level, non-application specific functions like Lucas Canade tracking, like edge detection, like the Huff transform. There are also higher level libraries. For example, Soft Kinetic, which makes a 3D time of flight image sensor, also provides gesture recognition middleware that takes the depth image from that 3D sensor or from a different type of 3D sensor like a stereo sensor pair, and extracts gesture information using the depth image from the sensor and skeletal models of how the body is structured, especially hands and arms, and how it moves, to output gesture information, so much higher level than these low-level building block libraries. And there are yet higher level, very application domain specific libraries. And probably the best examples of those are in the augmented reality realm. If you go over to Augmented World Expo and their exhibit floor, you'll see probably a dozen different companies offering SDKs for augmented reality application developers, some of them quite high level, really abstracting away all the details of the underlying computer vision algorithms and enabling application developers who don't know much about computer vision and maybe don't want to know much about computer vision to write applications that do things like recognize objects and track them and orient the handheld device in a room by identifying the floor and the walls in the room. Similarly, in the machine vision space for factory automation, there are a number of these domain-specific libraries. One is LabVIEW Vision from National Instruments, which is specifically oriented towards these kind of factory inspection and factory automation applications. The last category of tools I want to talk about are development kits. Again, with the proliferation of processors targeting vision, there's been a proliferation of development kits, including some very low-cost $100, $200 development kits targeting vision. And I think this is really a boon for product developers. In the best case, when these kits work well, they deliver some really good value and capabilities, including not only giving you the chance to experiment with and get a flavor for what the processor and its tools can do, but also enabling you to start experimenting with how the choice of a processor and the capabilities of the architecture and tools might affect your choice of algorithms. For example, Goxel talked about the use of fixed point. If you know you're going to use fixed point because you're going to use a fixed point processor for maximum energy efficiency, that might affect what sort of algorithms you're going to use. And maybe you're not going to do matrix inversion, for example, which doesn't tend to work very well in fixed point. Also, these development boards enable you to start getting your algorithms and your prototypes out into the real world so that you can do more testing. And that's often really critical for vision applications because they need a lot of testing under real world conditions so that we can get confidence that they're going to hold up in actual use. So to wrap up, what we've learned from our work with these kinds of vision tools and others over the past few years is there are lots of different tools of lots of different kinds. It's not like there are 6 choices for a C compiler like 10 years ago when we were doing typical embedded software projects on an ARM or an x86 processor and you knew you were going to use a certain set of tools, just a question of vendor A's compiler and debugger versus vendor B's. Here we have lots of different kinds of tools and APIs. We have OpenCV, we have OpenCL, maybe OpenVX, we have processor-specific building block libraries, development kits, etc. It's a pretty complex and potentially confusing landscape. And the choice of tools has big implications. Choice of tools has big implications in terms of what your programming style is going to be like, what kind of processor you can use efficiently, how efficiently you're going to be able to use that processor, and so on. And so this brings me to, I think, one of the most important points, which is it can be very helpful to think early about what the target processor is going to be, even when you're in that very early prototyping stage, not using the target processor, but just running on a workstation and trying things out. Because the choice of the processor often implies a choice of tools, and that choice of tools has upstream implications in terms of what kinds of algorithms are going to work well, what kind of programming style is going to work well, and so on. For libraries, source code is really valuable. OpenCV and other open source libraries include source code. Some commercial libraries do, others don't. And with more and more developers tackling vision projects for the first time, resources that enable people to get started quickly and efficiently get up to speed are really valuable. And those include things like full working application examples. So when I get a development kit, I really want to see at least one and preferably several fairly sophisticated, documented, full working applications that I can run out of the box with source code. So I can really see how a real application works on this platform, rebuild it through the tools, start modifying it, and in that way get myself up to speed much more quickly than if I was starting with a blank sheet of paper, trying to figure out how to get my first program to compile. So what we'd like more of, we'd like more tools like OpenVX that can deliver on what OpenVX is promising. For example, and specifically, relaxing this trade-off between developer productivity and portability on the one hand and efficient implementation on the other hand. We need efficient implementation to make our products practical, but we'd like to get it without giving up too much in terms of our developer productivity and portability from processor to processor. We'd also like tools to help us evaluate algorithm choices. There are lots of algorithm choices, lots of sub-choices of parameters, and often a lot of exploration is needed to figure out what are the best choices there. Currently, there aren't many tools to help with that. And also, I think we need resources to help developers choose tools, given that's kind of a confusing and fast-moving landscape. And that's the kind of thing that the Embedded Vision Alliance is doing, and I think we'll do more of going forward. I've got some resources listed here. By the way, all the slides from all the presentations today will be made available to you in the next few days on the Alliance website, and you'll get an email indicating where you can download them. Here are some places you can go on the Alliance website for more deep dive discussions of specific tools and design techniques. Thanks.